So the enhancement of the effect of design parameter on the on Rankine cycle. Uh, I'll discuss. We said like the Carnot cycle is more efficient than the Rankine cycle, and it is for the reason like that the temperature at which the heat is supplied in a Carnot cycle is much better, much higher than the temperature at which the heat is supplied at the Rankine cycle. Or in other words, the average temperature or the mean temperature of heat addition of the Carnot cycle is much better than the mean temperature of the Rankine cycle. We can enhance the mean temperature by two of the processes, and one is we call it as a superheat, and the other process is called as the reheat process. So what actually superheat process is what actually is the superheat process. So moving back to the ideal cycle and moving back to the normal cycle, saturated cycle. So when we said like we start our Rankine cycle, we started the Rankine cycle previously at state one, and which was actually at the saturated state. It is still possible, like at state one, I can supply more heat in a boiler, and rather than actually leaving it in saturated state, I would actually move it to the superheated state. So when I'm moving in a superheated region, I have increased the temperature, and once actually I expand it, it will be expanded in a state 2 dash. Let's say I've moved from 1 to 1 dash, and then I've expanded to 2 dash. Now there is actually a two advantage, or I would say like 2 to 3 advantage of this thing. One, I've increased the average temperature. What actually I mean, like now I would be having a temperature on this temperature, this, this, and obviously this. So if it is previously, if the average temperature was somewhere here, now it will be improved a little bit more. So one thing actually, I've increased the average temperature, and that average temperature I've increased the area enclosed in a TS diagram, which mean like I've increased the work done as well. And you can also find it like before it was actually enthalpy expansion from this state to this state. Now there is an enthalpy expansion from higher state of the enthalpy to a state 2. So this is what actually we have got, like the work done will be increased and obviously the efficiency. Also, there is one more advantage of superheat process, and which is actually in a normal cycle, saturated cycle, the expansion was at state 2. Now the expansion is at state 2 dash. There is much more, the quality of the gas exiting the turbine is increased now, while in this case at in normal cycle it was at state 2 over here, which means like we were having a reduced quality. So by increasing the quality, that means like we are increasing the performance of the turbine. In other word, what we are saying, like when the gas is exiting the turbine and with the less moisture content as a mixture, there is advantage in terms of decreasing the mechanical deterioration of the blade. That means like when you are having expansion, and there is actually a moisture in a turbine, so that deteriorate the blades, and also deteriorate the also the oiling of the turbine, the greasing of the turbine. So that means like in terms of mechanical, so you have improved the performance as well. So in that mean like you are increasing the average temperature as we have said, so you are going towards the efficiency of the Carnot cycle. So compared to basic cycle, superheat has increased the turbine work, increase the main temperature at which the heat is added, and also increase the cycle efficiency. Now there is another cycle, and we call it as a reheat cycle. So now when we are saying like we have increased the thermal efficiency, or we have increased the average temperature in a superheat cycle, there is a little, we would say, like added disadvantage to it as well. We would definitely not call it as a very much disadvantage, but yes, obviously you can think about it. When I'm expanding the gas or the steam from state 1 to state, let's suppose this one, so there is actually quite a big expansion, or enthalpy drop is increased now. And when the enthalpy drop is increased, obviously we would need a bigger turbine also, and also there can be an inefficiency in enthalpy drop as well. So it is most desirable like we would compound it, and that is we would, rather than actually expend the enthalpy in single stage, or the pressure in a single stage, we would expend it in a multiple stages. So that is when we would actually put a concept of a reheat. So what actually the concept of reheat is, let's say same thing, we are expanding from state 1 in a single stage of the turbine, sorry, the first stage of the turbine. So when I'm expanding from state 1, I would expand to not to the condenser pressure, but to the pressure which is actually lower than the higher pressure, but somewhere above than the condenser pressure. So I'm not actually expanded fully to the condenser pressure, but to a lower pressure than the maximum pressure of the turbine. So that means like I'm expanding from state 1 to state 2 in a first stage of the turbine. Once I'm at the second stage, sorry, at the state 2, I would actually reheat the steam again with the pressure which is at the exit of the first stage. When I reheat it, I would raise the temperature over here to a superheat, possibly, and then I would expand it again. So now the thing is like, on a reheat cycle, again I have increased the area under the curve. Again I have increased the average temperature, and also again I have increased the moisture content. Or sorry, not increase the moisture content, but increase in the dryness, and reduce the moisture content. So that means like my reheat cycle is again a little bit going towards the efficiency. But over here, if you have noticed, like there would be a little bit heat, much heat added to the system. That mean like in a previous cycle, we were supplying only heat from, let's suppose, 6 to 1 now. Now in this case, we are again supplying heat from 2 to 3, and that is actually in a reheat process. But the work done which actually we are getting is actually from 1 to 2, and again from 3 to 4. So this is what we call it as like, although there is actually increase in a heat supply, but the process is such optimized, like what we call it like the reduction in the sorry the supply in a heat is less than the advantage which we are getting in terms of work done. So this is advantage of, again, advantage of a reheat cycle. Uh, in terms of efficiency, in terms of the finding the efficiency, so that now that would be, efficiency would be equal to the work done from 1 to 2 in this scenario I'm talking, plus work done from 3 to 4 minus work done from 5 to 6, which is actually the pump work, divided by the heat supplied, which would be heat from 6 to 1, plus the heat from 2 to 3. So this would be the efficiency of the reheat cycle. Uh, Comparing the comparison of the Carnot cycle and the Rankine cycle with superheat, that's been given in the figure 1.4, and the reheat cycle is given in figure 1.4. Both of them would increase the power output of the cycle. Both of them would actually elevate the problem of having moisture in the turbine, and both of them would actually increase the average temperature of the Rankine cycle, and that's why it is actually enhancing the efficiency of the Rankine cycle. Um, Now the question is like the isobaric process in a Rankine cycle is also the isothermal process. In other words, the temperature at which the Rankine cycle is working, the maximum and minimum temperature at which the Rankine cycle is working, is controlled by the pressure, inlet pressure, and the exit pressure. Or in other words, the maximum pressure and the minimum pressure, and that mean like the pressure of the condenser and the pressure of the boiler. So in that case, if I would say like decreased the condenser pressure or fixing the boiler pressure, I would increase the thermal efficiency. Also, if I've increased the boiler pressure, I would increase the thermal efficiency. So how much the condenser pressure would be reduced? So in an ideal case, normally the condenser is kept at a atmospheric condition or 1 atm. Sometime like a shell and tube condenser or barometric condenser, naturally it will go to the vacuum pressure, and that vacuum pressure would normally maintain. But more or less it is nearly to the atmospheric condition. It is because also like if you want to decrease the pressure, you would be installing a vacuum pumps and so on and so forth, so that would be added power to the system, and we would not require that one. So the condenser pressure is normally kept at 1 atm or the atmospheric condition, so that's why the condenser pressure is at 1 atm, while the boiler pressure depend on the enhancement in the uh, uh, material research or material advancement. So more the material can sustain the pressure and temperature, the more the boiler can actually go to the pressure, the more high it can go to the pressure. But now in current technology, the boiler can go up to the critical pressure and can go up to as much as 600 degrees centigrade pressure. So now we can have a supercritical condition, and in a supercritical condition, that mean like in a supercritical boiler, that would be our maximum boiler pressure or boiler temperature at which we can achieve, and that mean like we can actually go to in terms of enhancement and in terms of efficiency, the maximum can be possible in a supercritical boiler. I hope like you understand these concepts, the basic concepts of the Rankine cycle. If you still have got any question left in your mind, you can post it in your Google Classroom, and I would be definitely able to answer that one. Thank you very much. Have a nice time.